we're starting recording again in a moment, and we'll continue to talk about muscle contraction. We'll get there in a moment, hopefully. Okay, we're recording. Back to the PowerPoint. So we said that when a muscle contracts, you can see the length of the sarcomere at rest is overlapping myosin with actin. Somebody has the microphone on, please turn it off. I hear all this background noise. So, okay, so this is a sarcomere. The sarcomere is going to shorten by the actin filaments being pulled in and getting closer to the M line or the H zone. And when that happens, the muscle fiber, the muscle sarcomere gets shorter and the whole muscle fiber contracts. So this is a list of what happens. Voluntary muscle has to receive a nerve signal or an action potential. The neurotransmitter acetylcholine is released and binds to receptors. When acetylcholine binds to receptors, we'll see that sodium moves into the muscle fiber. An action potential starts in the sarcolemma. It leads to action potentials in the T-tubules. And when the T-tubules have an electrical signal moving in their lumen, calcium is released into the sarcoplasmic reticulum. Every muscle fiber, muscle cell has a neuromuscular junction, meaning it's a synapse. So it's the joint, the nerve is very, very close to the motor end plate and has a synaptic cleft. On the motor end plate are acetylcholine receptors. Acetylcholine can bind, and after the muscle contracts, acetylcholinesterase has to be removed. So here we have a neuromuscular junction. The yellow is all nerve. Axons are split into various branches, and the neuromuscular junction is the nerve just at the synapse, and the motor end plate is just below the synapse on the surface of the muscle. So nerve joins with muscle, and each muscle fiber is going to have neuromuscular junctions because these fibers cannot contract unless they are stimulated by a nerve. These are voluntary muscles, most abundant in the body, everything from your biceps, triceps, gastrocnemius, and so on. All these voluntary muscles allow us to maintain posture, walk, run, move around, okay? So at the neuromuscular junction, we have the nerve, which has vesicles that contain acetylcholine. So when the nerve impulse or the action potential comes down the axon, these vesicles with calcium moving into the calcium will move into the nerve endings of the axon terminals, and acetylcholine is released when these vesicles merge with the cell membrane. Acetylcholine is released. This acetylcholine binds to the channels, and the channels open, and sodium is able to move in. And once the action potential spreads across the action potential is moving all along into the muscle, into the sarcoplasmic reticulum. And remember, acetylcholinesterase removes acetylcholine because we want the muscle to react, because it'll rest, and then very, very quickly it can contract again. So when an action potential or nerve spike comes to the end of the nerve, calcium rushes in. This picture doesn't say that, but calcium has to move in through calcium channels. Acetylcholine vesicles fuse with the membrane. Once they fuse, they release acetylcholine into the synaptic cleft. So this neuromuscular junction is nerve, synapse, muscle. This is the motor end plate. Once the acetylcholine has fused with the channels are open, sodium moves in. The internal muscle just below the neuromuscular junction becomes positive, and this sodium begins to spread throughout the muscle fiber. And once that happens, acetylcholinesterase is going to quickly remove acetylcholine so that the muscle can relax and be ready for contraction. Okay, so we'll read through these, and I'm going to talk about what's happening. So a resting sarcomere has myosin heads, and they are energized by ATP. So remember, the actin completely surrounds the myosin. The myosin has all these heads, and once calcium is released from the sarcoplasm, it binds to troponin, which allows these tropomyosin filaments to rotate and expose binding sites on the actin to allow this energized myosin head to join. So let's repeat that. So remember, the actin is made of globular proteins. There is this long filaments, tropomyosin, and the troponin is there to bind with calcium, because once the nerve spike comes into the muscle and it gets into the inside of the muscle fiber and into the sarcoplasmic reticulum, that is going to release calcium. That calcium is going to bind to the right here, the calcium binding to the troponin. That's going to cause rotation of these tropomyosin fibers to allow the myosin head to attach to the myosin heads on the actin. Once that happens, the myosin heads will use their energy they got from ATP, release adenosine diphosphate with phosphate. So notice that the myosin head pivots. Notice the position here with ADP and phosphorus, which is energized the myosin head. It pivots toward the center of the muscle. It detaches, and the process will start all over again with the myosin head being energized. So when this myosin head pivots from its position just before contraction, notice when it pivots along its hinge, it's going to cause the actin to be pulled into the center of a sarcomere. So we get a closer look at the contraction process. Let's stop there, go back to here, and stop recording. Stop recording.